no, I think we are.
Anyway,
So we
Kernel
always take
Design.
to the beginning.
Yeah, it was not used to the command.
No, exactly.
And we got started with a theoretical question 2. We were there like struggling. We lost out of time then. It was nice.
Yeah.
It's good to have it there. Other day you can
Yeah.
move with more time.
Okay, thank you. So I'm very happy to have Nicolas Durrande here. So Nicolas was before based in Etienne, and now he moved to Cambridge.
Yes.
He changed the nice French weather for the beautiful English weather. Yeah. So
Look at that.
so he's going to talk about kernel design, and welcome and thank you.
Thank you, Mauricio. So, yeah, I'm going to talk about kernels. We've seen this morning 2 introductions. I'm going to make a 3rd introduction to Gaussian process models, but that will be very short. And then I will focus a bit more on what's this covariant function and how we can play with this covariant function to make models more interesting. So, what people have explained already this morning is that the distribution of a Gaussian process is specified by 2 things. The first one is the mean, which is a function, and the other one is the covariance, that is a function of 2 variables, and that will tell you what is the covariance between your GP evaluated at one point and your GP evaluated at the other point. So this covariance function is the one that I call kernel. I use the 2 exchangeably. So we assume that we have a function, that we have a few observation points of this function. So this is our data, and we want to use this data to make some predictions. So for example, I want to look at in one point that I have not observed, what would be a plausible value of the function at this point, given the other observations I have around. So now if we just look at the data and if we make no additional assumption, then we can't predict anything about what's going on there. If we assume the value of our function here to be unrelated to the other observations, then we can't predict anything. So we can't predict, we can't make models without making assumption. And in Gaussian process models, the assumption that we make is that the function we want to approximate is in this set. We say that the function I want to approximate is one of the sample of my GP. So here you can generate as many samples as you want. How can you combine this assumption you make with this data you have? So we've seen this morning the Bayes rule, and that's one way to write it. What would be another way to combine these 2 information with the data and this assumption? Yes? Yeah, exactly. That would be the way to go, to do some filtering and to remove basically all the sample paths that do not go through our observations. And that's another point of view to see the conditional distribution of a Gaussian process. We just get rid of all the sample that do not make sense according to the data we have. And this is basically the model we obtain in the end. So here you can see all the conditional samples, and what has been discussed this morning is that this is still a Gaussian process with a different mean and a different covariance function compared to the mean and the covariance function of our prior. So this would be the prior distribution, and this would be the posterior distribution. So it's not very convenient to work with this sample, and in practice, that's really not what we are doing. We are never generating as many samples as we can and getting rid of the ones that do not interpolate. That's not the right way to go, but it's a nice way to see it. And in practice, we usually work with the mean value and the confidence intervals around our models. So we know that 95% of the functions I was plotting in here would be here inside these confidence intervals, right? The notations I'm using, maybe I will take some time just to make sure no one is confused about it. I write the mean predictor this way times the observation f. So this will be the shape of the objects I'm having. So this is a vector that contains the covariance between the point I want to predict and all the points I have in my data. So if I have n points in my data sets, that would be n. If I have just one prediction point, that would have one line, n column. This will be n lines by n column, and this will be 1 by n, right? So this is a matrix notation for the kernel functions, all right? So we can see that these expressions, they basically only depend on the kernel. So we can already tell that the kernel will be something very important for the models we are building. And if we change the kernel, we will change completely the model we end up with. So what is a kernel? Something we can see directly is what are the consequences of the property of the covariance on the kernel. So first of all, if we look at the kernel evaluated at x and x, so this is the covariance between z of x and z of x. So this is a variance, so this has to be positive. Another thing is we know that the covariance is symmetric, so the kernel function has to be symmetric too. All right, you can't have a kernel that is not symmetric. That's not a valid covariance function. We can obtain a thinner result and proving actually that the kernel has to be positive semi-definite. If we look at this random variable, so you take a GP, you evaluate it in some points, and you construct a random variable like that. So from I equal 1 to n, you fix n as you want, you pick the points you want in the input space, and you make this linear combination. This will be a random variable. That will be, this is a random variable, so the variance, whatever the n we pick, whatever the x we pick here, we know that the variance of t has to be greater or equal than 0. And if you compute the variance of t is also equal to the double sum to this quantity. So this is the definition of a positive definite function, and a kernel has to satisfy this property because this has to be interpretable as a variance. Okay, so every kernel will satisfy this property. On the other hand, any function that satisfies this property can be seen as the covariance of a Gaussian process. So there's an equivalence between these two things, being positive semi-definite and being a covariance of a Gaussian process. All right, so this is the two requirements for a kernel, being symmetric and being positive semi-definite. Any function that satisfies these two properties, you can plug it into a GP model and then interpret this model as usual GP models. So if you open textbook, you will end up with plenty of covariance functions that we know are positive definites. It's not something that is very easy to prove, right? Because if I give you a function, if I ask you to prove me that this is greater or equal to 0, whatever n is and whatever the point x here we pick, it's very difficult from this definition to prove what we want. But for all these functions, we know that they are positive semi-definite, so we can plug them into the models and we'll end up with something that makes sense. If the kernel depends just on the difference between the 2 points where it's evaluated, so the kernel is called stationary, and you can see that we usually have 2 parameters for this kernel, one that is called the variance parameter and the other one that is called the length scale. Why is the first one called the variance? Because if you compute the value of the kernel at x and x, so if you compute k of xx, this can be interpreted as the variance of the GP at x, and k of xx will be sigma squared times this exponential of 0, so this will just be sigma squared. So sigma squared can be interpreted as the variance of the GP at any point of the input space. And so I have a short demo, but normally you've already seen that during the lab session. What happened when you change the value of this sigma parameter and the value of this length scale parameter? So if you change sigma, I'm not sure, can you read these parameters or not? So here the value of sigma squared is equal to 10. So you can see it's the value of the kernel here. The maximum value of the kernel is 10, and if I just set that to 1, just the axis is changing. So sigma is just a vertical rescaling of the kernel, and sigma is also, if you look at the sample from the GP, sigma will also be a vertical rescaling of the GP samples. Okay. On the other hand, if you change the theta parameter, so let's say this is 0.2, let's say we pick 0.5, this is another type of rescaling, but we are rescaling the input domain, right? If we look at here where the parameter sigma appears, it always divide x minus y, all right? So it's just a rescaling of the input space, whereas sigma is a rescaling of the output space, okay? So we can usually parameterize kernel by these two parameters. Do you have any questions on that now that you've used them during the lab? Yes.
I have a question about positive semi-definiteness.
Yeah.
Why do we need this semi? Because actually it doesn't work, because then we have some kind of singularity.
Yes.
Not convert to matrix if it is kind of semi-definite.
So the thing is, when we say semi-definite, it actually allows one of the eigenvalue to be equal to 0, and the matrix in here are not invertible anymore. But you can replace this inverse by pseudo-inverse, and then your model still makes sense. So actually, we should write all the time pseudo-inverse over there, or use pseudo-inverse when we are making this inverse, right? It's very easy to construct something where you will have a 0 here. If you consider for t equal, let's say, z at 0 minus z at 0, this is a linear combination of the GP, right? And this is just equal to 0. That's not very interesting, but this is a random variable that will have a variance 0, right? So it's easier to think that everything is positive semi-definite, and then to use pseudo-inverse and to ignore the null eigenvalues. Okay? So if you plot the kernels, and you've been doing that during the lab session, you can see that they can have very, very different shapes. So it's not very easy if we just plot a function to say, is this function positive semi-definite or not? There's no easy way to prove that. But there's a big variety of functions that can be used. So for a few kernels, we can actually prove directly from the definition that they are positive semi-definite. If you try, for example, with this kernel, if you write the definition over there, then you will end up with this quantity being equal to 0 if I and j are different. So the double sum will actually only be one sum over ai square, and we know that this is greater or equal than 0. So for a few kernels, we can use directly the definition to prove they are positive semi-definite. For the others, it's more tricky. There's one very interesting result, that is the Bochner theorem, that states that any stationary function, so if a kernel is stationary, so if it writes as a function of the difference, then there's an equivalence between this being positive semi-definite and this being the Fourier transform of a positive measure, positive finite measure. So proving that a function is positive, that's something very easy. You just check for each x, is it positive or not? And using this trick, so checking that this function is positive and finite, which is easy, then ensures that this guy here will be positive semi-definite. So we can use that to create a first kernel. So if we consider this measure, so it's equal to 0 everywhere except between two values where it's equal to 1. This is positive. This is a measure with a finite mass. So if I take this Fourier transform, I will obtain here this function, the sinc function. And we know that this can be used as a kernel because it is positive definite according to Bochner theorem. Right? So you can build Gaussian process model using this at the kernel if you want, for example. Okay? So this theorem is very helpful if you want to prove that usual kernels usual stationary kernels are positive semi-definite. For example, we know that the Gaussian is the Fourier transform of itself. A Gaussian is something that is positive, so the Gaussian is a positive semi-definite function. And the Maten kernel are the Fourier transform of these type of functions with the value here that changes depending on the order of the Maten kernel you're looking at. And so this is positive, so we can use the Maten kernel into our models. All right? And you can also use this property to build new kernels. So this is a work from Andrew Wilson. And he's thinking, if I want to create a kernel, it's easier to create a positive measure, and he's creating a positive measure by taking sums of Gaussians that have a mean and a variance parameter. So he has a few parameters to parameterize this sum of Gaussian, which is actually the thing. He's going to compute the Fourier transform to end up with this kernel in the end. And now we know that by construction, this is positive semi-definite, so you can use it, for example, to generate sample path from the GP, and this is what you obtain. So there's one interesting thing to see here. So I don't have any labels on the y-axis, but this would be the 0 value. And you can see that this function is positive definite, but it can take negative value, right? It's not because you're positive definite that you have to be positive everywhere. This function takes negative value, but still it's positive definite. It just means that the value of the GP in one point is negatively correlated with the value of the GP a bit further away. And what happened in the sample path when we look at them later is we obtain these samples that are quite wiggly. So they are not periodic, we can say that, but they behave, they are wiggly. So this can be an interesting covariance. For example, if you want to approximate waves coming to the shore, you know you will have some kind of periodicity because there will be one wave after each other, but the period may change, you will have some phase that will change, so on and so forth. So this could be interesting to model this kind of phenomena that are more or less periodic, but not exactly periodic. So we have seen there are many kernels that exist, that those kernels depend on parameter. Maybe one thing I should detail before going much further is the effect of the kernel parameters on the models. Normally that's something you've seen during the lab, but I will just make the demo over here. So I will revert here to a smaller value of the length scale, and I will just consider a few observation points. And this is, so the posterior for a Gaussian process model with a Maten kernel, a 0 covariance, a variance equal to 1, and a length scale equal to 0.2. So if we decrease the length scale over here, I'm going to decrease it even more. If I take a very small length scale, this is the kind of behavior we end up with the model. Can you understand why the model behaves this way? What does it mean to have a very small length scale?
It's a local fit, right? You're doing a local fit, and then the rest is just a standard deviation of
yes. Data. And why that? Yeah.
Because when you build the covariance matrix, then covariance drops to 0 really fast when it's far away from any of the points. So it goes to the mean, which is 0.
Yes. So another way to look at it is not to look at the model, but to look at the prior we have for this value. And this is the kind of prior we have. With very small covariance, it means we kind of contract a lot the input space, and we have a very, very wiggly process. So when you're doing a prediction about what's going on in this point, it says, well, I have informations that are over there, but since my covariance decays, the decay of my covariance is very fast, then I don't expect these points over there to give me any information about what's going on here. So the model will revert to the prior and basically say, if you look at here, I can't predict anything about what's going on here because my information do not give me any information. So when you fit a model, it's always here it's easy because we are in one dimension. But if you have more than one-dimensional variables, it's always very important to look at the value you get after the optimization of your hyperparameters, because they will basically tell you what are the assumptions you're making about your model. And quite often, as Rich was discussing, you end up with bad values in the optimization, and your model may look something like that, which is very uninformative. So look at your model. If you have very small value for the length scale, even in one dimension, your model is basically telling you, I don't know anything because I will always, all your predictions you're going to ask me to do will be very far away from all the observations I have. So it's very important to look at this length scale parameter you have during the optimization. Do you have any question on that? No? Okay, so I'll keep going. We've seen the mean predictor really writes has the kernel has a huge influence on the mean predictor. So here for the same data point, if I just change kernel and optimize the parameter, I end up with two very different models. Is one of those models better than the other? Yes. Yeah, that's the good answer. The wrong answer here is to say I prefer this model because there's much less uncertainty in this one, so I would go for this model. But it really depends on what's the actual function you want to approximate. If the function you want to approximate is like that, then of course it makes sense to have this model as your predictions. But if the function you want to approximate has this shape, then the model you have on the left will be very, very wrong. It will be highly overconfident, and the decision you will take based on your model will basically be wrong. Okay? So there's no good or bad model. There's just model that is suited to the data you have or that is not suited to the data you have. So that's why it's important to validate your model, so to compare the predictions of your model with other values to make sure that your model actually makes sense. So now if we have data and we want to make a model, then we'll have to make some assumptions about the thing we want to approximate. And the usual questions we should ask is the data I have, is the thing I want to approximate something that is stationary? So if I move through space, am I expecting to see the same covariance structure between my input points? The other thing is about the differentiability of the function we want to approximate. Is it something that is very smooth, or do I expect that to be continuous but not differentiable? It's the kind of question that is important to answer. Do we expect particular trends in our signal? So we usually take zero mean GPs. But if we know there's a trend that should have this shape, then of course we want to put that into the model. And do we expect particular patterns such as periodicity, cycles, or the function to have some properties like being additive, this kind of thing? And by answering this question, that will narrow the set of kernels that should make sense to the problem. So someone asked a question this morning about an automated way to choose a GP. Of course, there's way to do that automatically, but for me, it makes sense to make assumption and to be aware of the assumptions we are making when we are building the model. That makes more sense to me than just trying everything possible and picking the best one. The best one, if you try everything, the best one will very likely to be overfitting your data. So yeah, think about the assumption you can make, put this information into your model, and then use that. And to tune the parameters, as Rich explained this morning, we can maximize the likelihood of the parameters or minimize the prediction error. So that can be either on the test set or doing some leave one outs. So the thing is, the GP model does not only predict a mean value. So of course it predicts a mean value, but it also predicts these confidence intervals, and it also provides a conditional covariance between the value of the posterior process. So ideally, we want to make sure once we have a GP that the mean function is accurate, but we also want to make sure that the confidence intervals that are predicted by our model make sense. And we can also check that the predicted covariance, so for example, you have your GP that is fits on many points. You remove 2 points of the model, and then you predict what is the covariance according to your model between these 2 points, and you compare that by repeating the experiment to the actual covariance you have between the points you've removed. So there are many things that can be tested, but it's important not just to look at the mean, but to look at globally the whole model. Does it make sense? One of the thing I was first asking is the function I want to approximate, is it stationary? Most of the kernels I was showing before are stationary kernels. They were a function of the difference between the two inputs. And in practice, we like to work with this kernel because they have less parameters than non-stationary kernels, because then you have to characterize the non-stationarity. So we like to work with these kernels, but in practice, quite often the data we have does not come from something that is stationary. So a good thing to look at is some remapping of the inputs that will transform all our data to data that is more likely to come from something that is stationary. So to get good models, it's important to spend some time of input remapping and then using stationary kernels. Any question? Yes?
So you're talking about trying to capture the confidence interval makes sense, but how do you mean by makes sense? It's like, well, you see some obviously terrible thing or something.
Okay, so there's one easy thing that can be done. Where is the... Here it is. So let's say this is the data you have. You fit a model, you estimate the parameter, then you remove one of the points and you do some prediction without this point. So your model will be well, there's no reason for this, but let's say something like this. So this is your model, and by taking off this point, then you can compare the model prediction with the value you actually have. So the model prediction you have in here, if I do a cut, will be a Gaussian density centered on this value with a standard deviation that is given by your posterior distribution. So now you can take this error and you can divide that by the standard deviation that is predicted from your model. All right? And this divided by this standard deviation is something that is supposed to be n01. Okay? Now you can do that for all your points. So you do leave one out. You will obtain n realizations of random variable that are supposed to follow this distribution. And then you can, for example, plot an histogram of your epsilon that are standardized and plot on the same plot a Gaussian density n01. And then you will see if your model tends to be overconfident, underconfident, or about right. Okay? And a good exercise is when you compare an histogram, especially when there are quite few points, when you compare an histogram with a true density, it's always interesting on the side to compare a true density and an histogram of a sample from this true density, because I often see people that end up with an histogram, let's say that is like that, and they compare that to a Gaussian distribution that is like that, and they tell me, oh no, that's quite wrong, because here I was expecting these to be over there. That would be more consistent with the distribution, I hope. And I get a value that is over there, so that does not make sense. I should not be happy with my null hypothesis that these are distributed according to that. But if you actually sample from this distribution, let's say 20 points, and you compare that to the density, you will see there are usually some important differences between the histogram and the actual density you want to fit. So don't be afraid if the histogram does not look like exactly the density you're after. You just want it to be reasonable, and you can compare that to actual samples, an histogram of the actual samples. Okay? Any other question? Okay, so we've seen there are plenty of kernels that already exist, and we are going to see now that using these kernels as building blocks, we can create even more kernels and even more interesting ones. So this is basically the operations we can do on kernel that will keep their good property of being symmetric and positive semi-definite. So you can sum kernel together, you can multiply kernels together, or you can compose them with a function. When I talk about the sum and the products, I distinguish two things. I can either make the sum of two kernels that are defined over the same input space, or I can make the sum or the product of two kernels that are defined over two different input space to obtain a kernel defined over the tensor product of the space. Right? So I can sum two kernels depending on one-dimensional variables to obtain a kernel that is defined for two-dimensional variables. Okay, I'm going to explain that more in details in the slides. So here's a motivating example on summing kernel. You can find this example in the GPML book. So this data is the CO2 concentration that is measured in an observatory in Hawaii. And so here we have quite a lot of data, so I'm plotting it as a function, but if I were to zoom on a small portion, what we basically have is here data points that are like that. So there's one obvious thing we have in here is that we have a trend that sadly is increasing quite fast. And we also have these high frequency variations around it. Those variations are periodicity. The CO2 concentration is always higher during August in this observatory. And so we have a 1 year periodic signal on top of this trend. So now if we want to fit a GP, and if we consider a squared exponential kernel, we basically have two options regarding the choice of the parameter. We can either say, okay, I have a signal with high frequency variations in it, so I should choose a small value for the length scale parameter. And this is the kind of model we obtain that very quickly return to the mean value, because with a short length scale, when you are in 2020, you think you are not influenced at all by the past values. Okay. This model is quite bad. Maybe the confidence intervals are quite all right, but the mean value is very wrong. No one will expect the CO2 concentration to be equal to 0 in 2020. So we can be quite unhappy about this model. The other choice we can make for the parameter, especially the length scale, is to say, okay, I have this trend that corresponds to a low frequency variations. I'm going to pick a very large length scale to show what's going on, to take this trend into account. And now the mean is quite all right in this picture. We recover more or less what we would expect. But the confidence intervals are very wrong, because no one will believe you if you say, I'm very sure that the concentration will be into these confidence intervals over the next years. So for different reasons, but we can be unhappy about these two models. So there's no good parameter for this kernel to approximate this function. So the thing we can do is we can take, okay, so my signal is not as simple as a sample of a GP with a squared exponential covariance, because I have both small and large length scale in my signal. So I'm going to take the two kernels I had previously, and I'm going to sum these two kernels, and this is the kind of model we end up with, which is much, much better, because now the mean kind of makes sense, and the confidence interval also makes sense. So the prior we are having for this model is basically, we consider two GPs, one with a GP with large length scale. We are going to sum that with a GP with very small length scale. We also have a large variance over here and a small variance over here, because the high frequency variations have a smaller amplitude than the low frequency variations. So if we sum these two GPs, we will end up with something that looks more or less like that, and this is a prior that is much, much better than either this one or this one. All right, so just by summing kernels, we end up with a model that makes much, much more sense. It turns out that we have more parameters in this model because we will have 2 variance parameter and 2 length scale parameter, but the optimization turns out to be much simpler in this case. Those 2 models were quite degenerate, and that means that the likelihood will be very difficult to optimize, because it will always, for these 2 models, the likelihood will be very, very small, because any of these 2 assumptions makes sense for the data we have. So even if for this kernel we have twice as many parameters, the optimization will run much, much better, and you will have less problem if you have a prior that makes sense for the data you want to approximate. So we can do even better. We can say, okay, I've already improved by making a sum of 2 kernels, but I have more information about my signal. I know, for example, that there's this 1-year periodicity. So I'm going to fit a periodic, I'm going to add a periodic kernel on top, which means in your prior here, you're going to add another one with samples that are exactly periodic with a 1-year period. And when you look at the trend you have so far, maybe it makes sense to say that this is like a piece of a quadratic function. So we are also going to include in the model a quadratic term in the kernel. And this is the model we end up with if we do this sum of 4 kernels. Once again, we have more parameters to estimate, but they make more sense. So we'll have one here that will account for a quadratic trend, this one that will account for the trend for the low frequency variations, this one for the periodicity, and we add another one on top that is still one with high frequency variations that will account for the difference we can have from 1 year to another. We don't expect the signal to be exactly like a trend plus something periodic on top. We have some we have some other variations on top, so we can add a kernel with a small length scale in here. And we end up with something that makes sense and that we can use to actually make predictions. So summing kernel is something quite easy. You've seen in GPy, you just do a kernel 1 plus kernel 2. And you end up with a model that makes sense. So in a way, we are just specifying, we are just making the right assumptions about our signal by making right and precise assumptions, like I know there's something periodic, I know there's low frequency and high frequency variations. We are giving a lot of information to our model, and then the model can narrow its prediction to something quite precise that makes sense. Any question on that? Yes?
Yeah, maybe we'll get to this in a little bit. So in this example, it's very easy to look at this nice one-dimensional or two-dimensional data and see that it has these patterns and to choose the kernels.
Yes.
Therefore, is there any mechanism for finding a selection or a set to use in higher dimensional data where it can't be so easily visualized?
So my point of view is, so usually you're not the one generating the data. The data comes from someone, and you want this person to talk to you about the data he has and to give you as much as he can, or give you other data that may be related or something to get an insight about what's going on. So that's what I usually try to do when I get data to get the more information I can. If the person is an engineer, or if it comes from a numerical simulator, sometimes they are able to tell you information about if you can differentiate the quantity, because if it comes from physics, they have insight about how many times you can differentiate this kind of thing. But it's usually you're going to make hypothesis, and you want your hypothesis to be right, so just gather the more information you can. But no, there's no like magic way to get that automatically. Okay. So we can also make the sum of kernels that are defined over different spaces. So here I sum 2 one-dimensional kernel, one that depends just on x1, the other one that depends just on x2, to create a kernel over a 2-dimensional space. So this kernel, that is a sum of kernel, as previously, we can interpret it as the kernel of a sum of 2 independent GPs. So if we look at sample path from this kernel, then the samples are like that. So they are additive functions. So the sample can be written as a function of x1 plus a function of x2. So of course, this would be very interesting if you want to approximate a function that is additive. But they are also interesting if you want to approximate a function in very high dimension. There's all the theory on generalized additive models, all these methods. And this would be the equivalent in Gaussian process regression to the generalized additive models, just by picking a kernel that is a sum of univariate kernels. So here's an example. That's a test function that is additive. We have a bunch of observation points. And we fit two models, one with the squared exponential kernel and another one with an additive squared exponential kernel. And we see that this model looks much, much more like the function we wanted to approximate in the first place, because by specifying that we want the model to be additive, we give a lot of information to the model, so we end up with a better model. One interesting thing is that if you look at the mean predictor, when your kernel is a sum of two kernels, you can expand the product with respect to this sum, and you obtain these two sum models. So the posterior mean will be an additive function. And the other thing is that these guys can still be interpreted as mean predictor of a Gaussian process model. And they're actually right as a conditional expectation of a Gaussian process. So this is the expectation of the GP that depend on x1, given that we have observations of the GP in x1 that is corrupted by some observation noise given by what's going on in the other dimension. But these submodels can still be interpreted as posterior Gaussian process models, right? And if we look at the variance we have for our model, so this is very similar to what we had before. I just plotted it with less points to make the point more obvious. When you have usual squared exponential kernel, so this is the predicted variance, which is equal to 0 at the point where we have observations. And when you go away from the observations, then you retrieve the prior variance, because with rather small length scale, here you think you are very far away from all the observations, so they don't make any influence at all on the predictions you're making. So this is what we have for a squared exponential kernel. This is what we obtain for the prediction variance for an additive model, right? So we can see that there are some region of the domain, such as here, here, and here, where we have a small prediction variance, even if we don't have observation points. Why that? Because if we know that the function to approximate is additive, and if you know the value here, here, and here, these 3 points are basically the vertex of a rectangle. And for a function that is additive, if you know the value at 3 vertex of a rectangle, then you will know the value of the function over there. So that's basically what the model is telling. So you already told me that the function is additive. You gave me the 3 values, so I'm quite certain about the value here. I will have a very, very small prediction variance over there. So all this information you give to the model in the prior, you retrieve it in the posterior. Okay? And why are those models popular in high dimensional settings? When you have a lot of, when the input space dimension is high, it's because of this property that you can, even with a reasonable number of points, you can cover the space very, very well. So there's an assumption behind it that you're only going to extract the additive component of the function you want to approximate, but in high dimension, you already have a lot of degrees of freedom with additive functions, and with a number of observation points that just increases linearly with the dimension, you're still able to recover very well the function and to have basically 0 variance on the grid, even if you just have a number of observation that is linear with the number of dimension. Okay, if you want this behavior with 0 variance on a grid with a classic kernel like the square exponential or the Matten kernel, then you will need to be to have a number of points that increases exponentially with the dimension, which is something you can't do in high dimension, right? So we've seen about the sum. Yes.
So I have a question about these additive models. it seems like a pretty strong assumption, but
Yes.
then you can gain a lot by using it. So how do you test it a posteriori?
With this kind of thing, right? So you will look, you can leave one out, or better, you can have a test set on which you will compare what are the prediction of your model with the actual data you have. And you can't expect your model to be perfect, you just want it to be reasonable enough. And it's, especially in high dimension, it's not unreasonable to say, okay, my function may be too complex for me to grasp it, but I'm going just to grasp the additive component of it, and usually the additive component is already not that bad, especially in high dimension. But yeah, so after fitting the model, you do some tests. And ideally, you want someone to tell you, oh, I think I have two groups of variables, and I expect those not to interact, and I expect the function to be additive in these two components. So you can add kernel, like one defined over the first 5 dimensions, another one defined over the last 5 dimensions, and with knowledge or insight from the engineering guys. Yeah. So we've seen we can do sums of kernel. We can also do product of kernels. So here's, for example, squared exponential. This is a cosine function. The cosine happens to be positive definite. That's something that can be proven with the Bochner theorem. You make the product of the two guys, and you obtain something like that. You can also make product of kernels defined over different dimensions, and obtain new kernels. So you can use kernels as building blocks to create more fancy covariances. And another thing that can be done is to compose a kernel with a function. So this is very similar to having a remapping of the input space, because basically the kernel will only see the input through a function f. So this is very equivalent to making an input space rescaling. It's quite straightforward to prove that this is positive semi-definite. We can either use the definition of being positive definite, the kernel in here, so this sum of the kernel is equal to this sum of the original kernels in here. And if this one is positive semi-definite, it means that this will be positive whatever the values we have in the middle. So whatever the value f will end up with some value here that I can write y. And I know if k1 is positive semi-definite, then this will be greater or equal to 0. Okay, so this can be proven directly from the definition. Another way to prove that it is positive definite is just notice that this guy is the covariance of this GP. So if Z is a GP, I can construct this guy, and a covariance is always positive semi-definite. So that's another way to prove it. So yeah, that's a nonlinear rescaling of the input space. That's an example we can obtain. Let's say we want to approximate a function that is very non-stationary and that behaves in this way with high frequency variations around 0, and then lower and lower frequency in the variations. Then you can use the remapping 1 over x for the input space. You end up with a kernel that is like that. You notice that this kernel is not stationary anymore. When you move one of the variables in the space, then the shape of the kernel changes. But this is still a valid covariance function, and your samples end up being like that. And of course, all these transformations, they can be combined. So here's an example of a kernel. Why is that positive definite? It's because we have fx times fy. So this can be seen as a positive definite function. We know that k of x, y equal xy. This is a kernel. This is the linear kernel. I can do the composition of this kernel with a function. I will obtain f of x, f of y. I can call that k prime equal this quantity. I know this guy is positive semi-definite. And now I just have the product between two kernels. And this can be seen as a nonlinear rescaling of the outputs, depending on where you are in the space. So here you have very large variance around 0 and very small variance for larger values of x. So maybe I will skip this part because we don't want to finish too late, and I will just jump to the application. And the application is something I worked during my postdoc here when I was working in Sheffield. So we have some observations, and we want to extract the periodic component of the signal we have in here. So as we did previously, we're going to consider a GP that is a sum of two GP, one that has periodic sample path and another one that has sample paths that are not periodic at all. So what does it mean to be not periodic at all? It means that if you project that on the basis of sines and cosines, then you end up with 0, right? So it's a GP such that the sample paths are orthogonal to the sines and cosines function. So using some RKHS theory, you can prove that this guy is a kernel that will return periodic sample path, and this guy is a kernel that will return sample paths that are orthogonal to the periodic functions. And now we can look at a kernel that is the sum of these two guys. So our model, given this decomposition of the kernel, our model will be the sum of two submodels, one that is periodic and the other one that is not periodic at all. And we've seen previously that when we have these expressions, we still can interpret those as a conditional expectation. So quite naturally, we can associate a conditional variance, a conditional covariance prediction to the submodels that will reflect the uncertainty we have on the periodic or on the aperiodic components. And for the observation we had previously, so those are the observations. This is the model we obtained with the Matern kernel, and according to the expression I just gave, we can split this model as a periodic component and an aperiodic component of the model. So given the model, we can split it to extract just the periodic component of it. So now we're going to see we can do things a bit better. We initially started from a Matern kernel and we split it into a periodic and aperiodic component. Now that my kernel writes as a sum, I can decide to tune the parameter of the periodic component independently to the parameter of the aperiodic component. Right? This is positive definite. I can play as I want with the parameter. This is positive definite. I can play as I want with this parameter. So I'm basically taking a kernel, I'm splitting it in two parts, and then I'm treating them independently. So I obtain a new kernel with more parameters that will estimate with maximum likelihood. And I can also introduce another parameter that is the period or the frequency I have for my periodic signal. And this is what we obtain after maximum likelihood estimation of the parameter. And this is actually exactly the function I use to generate the data, something linear plus sine function. So now let's see an example. We have some data that comes from Arabidopsis, and the idea was to study the circadian rhythm, so the natural 24-hour rhythm we have in all living organisms. And so basically, so the biologists, they keep track of all the genes they can measure for Arabidopsis, and they do one observation every 4 hours. They look at what is the concentration is messenger RNA, which is something that will measure the activity of each of the genes. So every 4 hours, they get an estimate of the activity of the genes. And in the literature, so you have this kind of data, and they specify what are the genes that, according to their methods, behave periodically, and what are the genes that do not behave as periodically. And so we fitted this kind of GP model to the data. So we basically fitted 22,000 models, and we look at, according to our model, what are the ones with a large periodic component, and we label those as periodic genes. And we end up, so we were agreeing on most of the predictions, but we also had a significant number of genes on which we disagreed with the previous literature on which one are periodic or not. And this is a graph of a figure of the genes that are labeled as periodic in the literature, but that are not labeled as periodic according to our method, and another one that is the genes that are labeled as periodic according to our method and not in the literature. So here we can't deny that there's actually a periodic component into this signal. So we can basically see a cosine function, but sometimes we have a lot of uncertainty, like a lot of observation noise around it, and by definition, observation noise is not something that is periodic. Or we have a model with a significant trend. And on the other hand, the model we get are model with very high frequency variations, so genes that every 24 hours will basically bang saying, no, we have a 24 period. And we believe these genes to be very interesting into understanding the circadian rhythm because they really behave like with a sharp clock ringing every 24 hours. So these couldn't be retrieved in the previous method because the previous method were only using one cosine function to identify the periodic genes. With the linear regression, you can't use a lot of basis functions because linear regression does not do filtering on the high frequency. So if you were to put a lot of periodic function with a lot of frequency, you will ending up with fitting basically the noise and having a lot of high frequency component in your signal. Since we have a GP approach, in our prior we naturally have a penalty for the high frequency variations because we started from a Maten kernel and we know that there are very few high frequency variations in Maten kernel according to the length scale we estimated. So we naturally have a penalty on the high frequency, so which means we can add high frequency variations in our model, and by default it will tend to avoid using those, and it will not avoid using the high frequency variations when he has a good reason not to. Okay, so as a conclusion, so the kernel, they have a huge impact on the model. The expression of the model really depends on the kernel functions. So we have to be very careful about choosing them. Quite often we can hear people saying, oh, I've tried Gaussian process regression and it does not work. And so we ask, what kernel have you tried? And they say, oh, I don't know, I've just used the default one. And yeah, that usually does not make much sense to just use the default kernel. So take time to understand what assumptions are associated with what kernel on the differentiability, on the stationarity, so on and so forth, to understand the assumptions you're making about the function you want to approximate. And according to the making new from old literature, then they can and they should be tailored to the problem at hand you want to do, such as if you want to study periodicity, then you can do that by choosing the appropriate kernels. And yeah, so there are various combinations that can be done that ensures you still are positive semi-definite. And there's this bit that I haven't discussed, but if you have a function that map any function to a function satisfying the property you want, for example, it's very easy to construct a mapping that from any function will create a symmetric function. And if you do that, then you just have to apply this to your GP, and that will give you a prior that will be what you want, a prior for functions that are symmetric. Okay. Any question? Yes.
Is there any famous kernel which analyzes low and high frequencies as well? Where I have just kind of a middle kind of regime for frequencies which are low?
No, you can. So if you remind the Bochner theorem, so that basically you can basically pick the spectrum you want, right? So you can build a kernel that will have no weight for low frequency, weight for intermediate frequency, and a weight for high frequencies too.
Yeah. So let's say I use a kind of Gaussian with a mean of let's say 10.
Yes, you will. You obtain a kernel that will be basically something like that. In this kernel, you have a lot of intermediate frequency that correspond to these frequencies over there. Okay, so that's a way to filter on both ends. Yes?
So the only way to test your confidence intervals is the method you mentioned there, or there are other ways that you can verify?
So people do other things such as they count the proportion of points that are not inside the 95% confidence intervals, for example. Another interesting thing to do is to remove 2 points in input space and to compare what's the actual covariance between these 2 points, the one predicted by the model to the one predicted by the model. So I would say this is doing that with leave one out, I would say is the most common way to go. Yeah.
So the definition of kernels by defining them under power spectrum is very similar to the wavelet transform and generating wavelets. Are you familiar with wavelets?
I'm not familiar with this way of constructing wavelets.
Properties, but I know that you have to define them over. I mean, if you're not familiar with definitions, it makes sense because I was going to ask you. So that specific definition there on the board.
Yeah.
Is a subset of a wavelet, which is a cosine envelope kind of thing. I was going to ask is whether wavelets would be valid kernels.
No. No. They're not positive definites.
Okay.
No.
Just because that
Yeah.
is a wavelet as well.
Yeah, but
It's complex.
yeah. There's no. Maybe this one is, but in general they're not. Like the R1, for example, is not.
Sure.
Okay. Is that the end of the day? Great. And just if you want to play with that, you have access on my GitHub page. If you want to play with looking kernels, tuning parameters, just go to my GitHub and you have that. It's a Shiny app folder.
I had a quick question, like at the end about the flowers. So